Okay, so we've seen one example of how we can use the derivative and apply it into an algebraic or geometric situation to find the equation of the tangent line right here. What we're going to do now is look at another example where we'll find a derivative, this time using the other definition with our second definition, the one that involves h. So just as a quick reminder, we'll remember that that definition looks like this. It's the limit as h approaches 0 of f of a plus h minus f of a. You'll notice I'm doing this from memory. Of course, I'm not looking at any resources next to my screen. Just kidding, but actually, yeah, this is definitely one of those things that you need to have memorized. You need to have both forms memorized. So anyhow, here is our h definition. We're going to see how this plays out algebraically, and we're going to see some things that are going to be pretty consistent with how our limits are going to work algebraically. So be noticing some of the algebra that happens. I'll try to point it out. These things will happen every time we're doing a derivative using the definition. So we want to find f prime at 3, where f of x is x squared minus 8x. That is the derivative at 3. So remember from our definition that we just wrote up here, that f prime at 3, sorry, this is f prime at a, that's what I wrote up here. So f prime at 3 would be equal to the limit as h approaches 0 of a is 3. So it would be f of 3 plus h minus f of 3 over h. Okay. So let's see what happens here. What we're saying here with f of 3 plus h is that we would take our function f up here and plug in 3 plus h. So to be clear, let's actually do this in a different color. To be clear, f of, that's a little thick, f of 3 plus h. What does that look like? Well, it means we're going to plug it in here for x, which means we're going to take whatever we plug in and square it, and then subtract 8 times whatever we plug in. So if I plug in 3 plus h, I'd have 3 plus h squared minus 8 times 3 plus h. Okay. If I plug in 3, that one's a little more straightforward. If I plug in 3, that's going to end up being 3 squared minus 8 times 3. And we'll compute that in a second. So what I want to do is show that substitution happening over here in our limit, our derivative. So we want the limit as h approaches 0 of f of 3 plus h. Well, f of 3 plus h means take whatever I plug in and square it, minus 8 times whatever I plug in. That's going to be the top left part of my fraction, minus f at 3. So I'm just going to use colors to try to highlight this a little. So I'm plugging in 3 plus h, and then squaring it. Then I'm multiplying it by 8. On the top right, I'm just plugging in f of 3. Maybe we could use an even different color here. Plug in 3 right there. Okay, so we have those two separate substitutions. And from here on out, I'm really doing basic algebra. Maybe you've heard me say this. I definitely say it every year. The bigger challenges for a lot of us in calculus will not be the calculus ideas, but making sure we execute our algebra correctly. I've been harping on you for 2 years now to make sure you know algebra. Hopefully, you're feeling ready for this. So we just need to do some basic expanding of powers here, distribute, combine like terms, etc. And hopefully something will cancel. Although I suppose, but first we should check and see what's going on here. I'm finding a limit. So what's my first instinct for finding a limit? Right, I would try to substitute. If I substitute, real quick, we can see I get 3 squared, 0 plus 3 is 3, squared is 9, minus 8 times 3 is 24. F of 3, we didn't compute it over here, but it's going to be 9 minus 24, which is negative 15. Sorry, excuse that. Just checking to make sure I have my computation right. So f of 3 is negative 15. If I go back here, I said I had 9 minus 15, minus 24. 9 minus 24 is negative 15. And I'm subtracting negative 15, so negative 15 minus negative 15 is negative 15 plus 15, which is 0, of course. And obviously I have 0 when I plug in 0 for h in the denominator. So just to make sure, we always still want to check substitution, but we can be pretty confident that that's never going to work when we're doing a derivative by the definition, okay? So we should always be checking by our substitution, but in truth, when we're doing the derivative by the definition, we really don't need to check that. It won't work. That's why we're doing the algebra that we're doing. So anyhow, continuing on here, we just need to do that expansion here. Let's hope we remember how to square a binomial. Remember, when we square a binomial, we don't square each term, but rather it's 3 plus h times 3 plus h. When we square that, we'll get 9 plus 6h plus h squared. Feel free to do that off to the side if you need to. Then we're subtracting. Now be careful here, because we're subtracting 8 times 3 plus h, which would be minus 24 plus 8h when we distribute, but the whole thing has to be subtracted. And we already established that f of 3 is negative 15. We'll simplify that in a little bit here. So now we're just working on simplifying that fraction. Right? I'll rearrange terms a little bit here as I go too, just to try to clarify things. So I have h squared. When I distribute this negative here, I'll have h squared plus 6h plus 9 minus 24 minus 8h plus 15. And hopefully you're noticing something here. If I scan my numerator for the constant terms, I have plus 9 minus 24 plus 15. And what do you notice about those? 9 minus 24 plus 15 equals 0. If you are doing your computations correct, this will happen. This is one of those patterns I was talking about. If you're doing your computations correct, the constants will cancel each other out. This is really critical because we're about to see what happens in the next step. If we now move on and combine like terms with what's left, all their constants cancel each other out. And we had h squared plus 6h minus 8h. So that's really h squared plus 6h minus 8h is minus 2h all over h. And hopefully we immediately notice that there is a common factor. So if I factor out that h in the numerator, that leaves h minus 2 all over h. And now I can cancel those h's. And I have the limit as h approaches 0 of h minus 2. And now, this is a really basic limit that I can evaluate using substitution. So I plug in 0, I get the limit is equal to 0 minus 2, which is negative 2. And there's our limit. And furthermore, there's our derivative, f prime at 3, the problem we originally set out to solve. So we can see some interesting things happening here with our algebra. Remember, if we're doing this right, all of these constants are going to cancel, and the other thing that's going to happen is that leaves us with only variable terms in the numerator that have that factor of h, which will be a common factor that can cancel out the h, allowing us to substitute the limit. These are two things that are going to happen every time we're doing a limit, or finding the derivative using this limit definition with the h formula. This is part of what we talked about. There's two different formulas, some of the value of one versus the other, and this h formula is really nice because this is going to end up working out the same way every time, whereas you could imagine in this x minus a formula, in order to get that denominator to drop out, a lot of times, or every time, I'm going to have to factor the numerator and cancel. So if you are somewhat averse to factoring, perhaps this is one option, but I know none of you are averse to factoring since you're all cool kids. Anyhow, there is one other way we can find the derivative using the second definition, the limit as h approaches 0.